First, the ball recoils at half of V naught and it returns back on its original path. So it bounces off. The rod's going to start swinging upwards, as you guys probably can guess. You can't get the angle by itself, but you can get an expression for the angle. Probably something like cosine theta equals is what I'll be looking for. It's a uniform rod, so its center of mass is at its middle. And it's a uniform rod spun on its end, so the moment of inertia is 1/3 ml squared. But it has mass 3m. Okay? See what I'm doing there? Just making sure we have an understanding. Next and last, your answer can only have G, L, X, V naught, M in it. Okay? And numbers if necessary. I am looking for your line of reasoning. There's a lot of algebra in this. Show me your line of reasoning. And if you're worried, you should be a little bit, but this was problem number 2 in the homework. And we talked about stuff like this yesterday. So give it a try. Let's see if you're... I think it should be done. There are alternatives, but not many. I think we need to break this problem up into parts. And so I don't want to throw away all of this, but I'm going to try and just reuse as much of this as possible so I don't have to do as much work. All right, so I think there's a part where the ball has recoiled and the bar has begun to swing. It has some velocity. I see this as what happens right after the ball bounced off the bar. Something in the middle here. And I think it's critical to understand that there's something important between these two parts of the problem. And then there's a part further into the future. In this next part that's further into the future, the ball has, moved away, but the bar has swung upwards. Now, this part no longer involves the ball. And a lot of you included the ball in this class, but energy nothing's happening to the ball after it recoils. It just continues with the same kinetic energy it had after it left the bar. But the bar's energy is changing. So it's going from one kind of energy to another. Its momentum is no longer being conserved because it's being acted on by some downward force at its midpoint. That force is causing a torque, so it's slowing it down. Now, none of that is in dispute. The knowledge here is that from here to here, the force it's acting on is gravity, so that energy is conserved. So I see two parts to this problem. I see a conservation of momentum part and a conservation of energy part. Now, you got to look at your work, folks. If you want the points, you want the AP graders to give you points, you have to convince them that you understand this. They're going to be kind enough probably to break this problem up into sections already, and kind of step you through. I didn't. But there probably will be something where they say, find an expression for the velocity of the bar after the collision. They might ask that as part A. Then part B, find the angle that the bar makes. They'll probably be nice enough to do that. But you can't count on that. You've got to anticipate. So the first thing I wanted to see is did you indicate that the angular momentum before is equal to the angular momentum after? Any indication of that would have been a great start. The problem is that some of you were able to indicate that, but you really didn't have, and I'm going to put the picture down below if you guys don't mind, because you guys need to be able to see what's happening, and if it's above, I lose half the board. So I'm going to try and start putting the pictures on the bottom, okay? The ball, it has angular momentum of a point mass. Nothing else is moving. Nothing else has angular momentum. It also has linear momentum of a point mass. Both kinds of momentum are possible here. The question is, are they both necessary? Well, the fact that the bar is held in place means that there will be an external force on the system. So linear momentum will not be conserved. I'm bringing that up because that doesn't have to be the case. You have homework questions where it happens on like a frictionless surface and there is no pivot point. So you have to be prepared for that. Don't assume they're all going to be like this. So I'm going to ignore the linear momentum here and focus on the angular momentum. After the collision, the ball is still moving. It has angular momentum still. And after the collision, the bar is moving, so it has angular momentum. It's a collision. These have to be equal. A big, bold statement of angular momentum. You guys, I know you want to jump and you want to start filling it out, you want to start putting things together. You understand that's probably worth a point right there. If we're trying to acquire points, stating reference to a known quantity like this is important. Because after this, you guys start making mistakes, and there's no clear line of reasoning after this. I have to come up with the angular momentum of the ball, R cross P. And I don't know R. Not right now. But in my head, I think we can advance this problem a little bit to the future. Right? We can advance it till just before it strikes the bar. In my head, that's what I'm doing. And recognizing that must be why they gave me X. So that I can use that as my R perpendicular. Which means MV for my momentum. If it's R perpendicular, I ignore the sign because it's a sine of 90 degrees. V naught, I guess. It bounced off at half the velocity. I don't have to redo my thinking here. It's x m times negative 1/2 v naught, guys. It bounced backwards. Now look, we've come to our first detail. Right? Little details. This is all really hard stuff. Trust me, really hard stuff. But this is a little detail. Knowing that first, it was 1/2 of the velocity. Most of you who got this far put the 1/2 in there. Making it negative, though, that's pretty critical. If it was traveling in the same direction, it would have passed through the bar. You follow me? But it bounced off, so we have to make its velocity negative. The bar, though, it's going to have angular momentum too. A lot of you got the angular momentum formula wrong. That's sad. There's only 2 letters there. But I had I omega squareds. I had all sorts of stuff. And I gave you I. I told you it was 1/3 ml squared. But I also told you the bar was mass 3m. So 1/3 times 3m L squared is just ml squared times omega. Some of you made some silly mistakes there. So a statement of conservation of momentum, and then I plugged in or used my expressions for angular momentum for each item there. I bet there's 1 point for knowing how to use the point mass formula, 1 point for using it again but subbing in half the velocity and making it negative, and 1 point for correctly identifying how to use the moment of inertia. I bet this is so far 4 points. If I was making an AP exam, probably. Because each one of these things is critical, and it's these little details that you get the points for. Now you have to solve for omega. That's algebra, the least interesting part of this, but necessary to solve the damn problem. And some of you can't add 1 to 1/2 and get 3/2. You're out there, guys. I know, I watched. But this becomes 3/2 xm v naught equals ml squared omega. So you do need to have an expression for omega. You cancel out the m's. We get omega is going to be 3x v naught over L squared, 2L squared. That's a lot, but I bet doing the algebra is worth a point. Questions to here? All right, so a lot of you didn't make it here. A lot of you. But a lot of you who didn't make it here knew you had to do something further. You recognize you can't find this answer, you still press on. If anything, I have to be really proud of the fact that most of you didn't give up when you couldn't find omega. You went and made sure you did something for energy, either because you had no place else to go or were bored or you knew I was going to look at it. But I was really happy to see that most of you tried to do something with energy, even if you didn't know what the velocity was. That's good. Perseverance is going to get you points. Because I bet the next step is for you to make a statement of conservation of energy. And almost everybody in the room universally did that. There's a couple problems, but the only thing we focus on here is the bar. Some of you focused on the ball, that's fine. But the ball's energy doesn't change, so you needed to include the ball's energy before and after. It just would have canceled out. Does everybody understand what I'm saying? Because the ball's energy didn't change. The bar's energy changes from one form to another. That's the only one we have to focus on. When the bar is rotating, it has rotational kinetic energy, and it will convert that into gravitational potential energy. But again, if you want to include the ball, you have to include the ball's translational kinetic energy both before and after, which is why it will cancel out. I'm saying that because I know there's like 4 of you who did that. Any question about why I'm not going to include it? Okay? So 1/2 I didn't leave much room to write omega, so let me back that up because omega is a mess. 1/2 I omega squared, that's all of this squared, 3x v naught over 2L squared squared. Oof, I know it's ugly, guys, I know. Equals mgh. Okay, we've made a mistake here, and it was a lot of you. It's the bar. Another detail, 3m. I know it's stupid, but yeah, they do that. They're going to do it on purpose. Now, we're almost at the end of the problem, but you're probably going to get a point for this, a point for subbing in the omega from the prior part of the problem, and a point for using MGH here. That's probably the way the point distribution will work. You guys have seen the grading documents. You know that I'm right. But at this point, we haven't worked in the angles, so we know we can't leave it in terms of H, which means we're probably going to have to do that L minus L cosine theta thing. Except you can't use L here. You have to use L over 2. The center of mass is located at the middle of the bar. It's the middle of the bar that's being lifted. So, although I think you have to do this substitution, you have to do it with L over 2. I bet that's 2 points right there. One for using L over 2 for the value of L, and one for subbing in that 1 minus cosine theta thing. All right, so at this point, we have just really ugly alphabet soup. So I'm going to write it all out. I might need more space. I'm going to try and be careful to make sure that all of it gets in there. Your job now is to solve for theta. 1 point. Right? This part, getting theta by itself, is only going to be 1 point. It's algebra. The worst part about this, though, is that's a lot of freaking algebra, isn't it? So, although, yeah, you might be asked to do something this ridiculous, and it's going to take us as long to do that algebra as all the other points we got for the prior part of this problem. So probably the 5 points that we would have gotten in assembling conservation of energy and doing it all correctly will come down to another part where you're going to do more time just doing algebra for only 1 point, which means never make algebra your priority, right? If you get to this point, you've probably got most of the points of the problem. Yes, you have to do algebra. If you have the time, get the algebra done. We have the time, so we'll get the algebra done. I'm going to combine some things. First, I'm going to realize I can get rid of this 1/2 with the 2 over here, and I can get rid of one of the L's with this L here, and I can get rid of the M here with the M here. Getting rid of all of that right off the top. I have a 3 squared, and I have a 3 on this side, so 3. I have an X squared, a V0 squared. I have an L here and an L squared squared, so L to the 4th. So that's going to be L cubed. And I have a 2 squared, so that's a 4. That's the algebra for this side. And that equals G times 1 minus cosine theta. Divide both sides by G, I guess. And now it's algebra, so I'll get cosine theta equals 1 minus this gargantuan nightmare. And it is a gargantuan nightmare. But this is kind of where I expected you guys to end up. Cosine theta equals something. Even if you made it this far, and some of you made it and had something different here, you can check your work. Not that you need to, but if you have 5 minutes left on the exam and you think you've got, this is the place to put your efforts, you can check. And I know how do you check? Well, you can't take the arc cosine of something that has any units in it. This side has to be unitless. And 1 is already unitless. So is this massive ugly thing unitless? The top has got x. X is in meters, so meters squared. V0 is velocity. That's meters per second squared. That's the top. The bottom has an L cubed. That's meters cubed. And G, which is meters per second squared. So when I look at the top, I see meters to the 4th. Look at the bottom, I see meters to the 4th. I look at the top, I see per second squared. I look at the bottom, I see per second squared. That's unitless. So I'm confident. You probably won't have that kind of time. But it's one of those ways to figure out whether what you have makes any sense at all. Now, looking at this, it's hard to know how any of these things affect it. What would make the angle bigger? What would make the angle smaller? All right, fun times. This is pretty thorough, but is there any questions that you have here that I can answer? Do you understand what I mean now by little details? That they're so critical, there's so many of them. But it's the little details where you earn your points. When you're looking at your work, can you follow your line of reasoning? Lay out something to follow. Some of you write everywhere, all over the place. I would encourage you to go vertical, start one line, and just move downwards on that line. So your grader has a way of looking for your line of reasoning. You have to provide them a story, something that none of you are doing. And you might want to start, write down what you're doing. Tell your grader, I'm doing conservation of momentum. Because remember, they're going to look for that. And many of you are jumping 3 steps ahead with a momentum equation. That works great if you're getting it right. But if you're not, tell them you're doing conservation of momentum. Let them know. It'll give them a place to start. At least they know that's what you're applying. You're not going to be able to fool the graders. You can't dazzle them with BS. They're just going to be too good. Yeah?
I'm having a hard time understanding why the ball has angular momentum. Like, especially like in the second picture, I guess, like when it bounces off. How do you know that it's angular momentum?
All right. That's a good question, and one that is at the heart of this whole thing. So if you guys didn't hear her question, she's saying she's struggling with the idea, how do you know the ball has angular momentum? So the ball has both. It has angular momentum and linear momentum. The better question, and you don't know to ask this, is how do you know which one applies? In this problem, the reason we know to use angular and not linear is the bar. Because the bar is going to rotate after this collision, it can only gain its rotational properties from the rotational properties of the ball. So we do the ball's rotational momentum relative to the bar's fixed point of axis. That's how we know. And we have to follow that throughout the problem then, once we pick it. Right. You have a problem in your homework where the bar isn't fixed, it's like on a frictionless table, and you'll have to use both. Right.